So I believe I had just given you all a table by which to calculate the piezo-resistive coefficient for single crystalline silicon when our strain and currents were flowing in a variety of directions. Okay. So earlier, we had learned, so let me just write here, piezo-resistive sensing continued. So earlier in class on Monday, um, you were given the relationship that your gauge factor is 1 plus twice Poisson's ratio plus E, which is Young's modulus, times pi, which is the piezo-resistive coefficient, right? So for single crystalline silicon, because the piezo-resistive coefficient is very, very large, the material property is going to outweigh the geometric properties. And so we can really just approximate this as pi times our Young's modulus. And I'm going to put as a note here for single crystalline silicon. Okay. And this simplification means that our fractional change in resistance, delta R over R, is then largely going to be dominated by the change in resistance along the longitudinal directions. That R looks shitty. And then some fractional change in resistance in the transverse direction, which would be then the gauge factor in the longitudinal direction times the stress in the longitudinal direction plus the gauge factor in the transverse direction, and then S transverse. Or alternatively, we could write this as pi longitudinal, so our piezo-resistive coefficient, times our, actually S is strain, so T is stress, sorry. T longitudinal plus pi transverse T transverse. So we can use either of these things or either of these relationships, depending on if the gauge factor is easy for us to find out or if the piezo resistance is easy for us to find out. So let's work a quick example. Okay. So let's say that I have the following microstructure. So on the left-hand side here, I'm going to have an anchor. So this is a solid portion of silicon that isn't able to move, flex, rotate, any of that kind of good stuff. And then we are going to have a cantilever beam like so. And then there's going to be a proof mass attached to the end of that beam, which will be undergoing some force. Okay. So here is our microstructure. Now let me hit you with some dimensions. So the length of our beam is 200 microns. The width of our beam is 20 microns. Over here on the right-hand side, we have our mass. So this is going to be thought of like a 50 micron by 50 micron square. obviously not to scale. Our force is going to be directed into the page in the middle of our proof mass. And then over here on the left-hand side, we're going to have two piezo resistors. So let me just kind of try to draw those in real quick. So we've got two piezo resistors, current flowing around the longitudinal direction on the beam. Okay. So before we actually get into anything, any of the math here, why do you guys think that the piezo resistors are located effectively at the anchor point or very close to the anchor point on this cantilever beam? So when we talked about stress and strain for cantilever beams, where was the maximum amount of stress? At the anchor. So if we put our piezo resistor at the anchor point, it's going to see the largest amount of stress or strain and therefore generate the largest signal. If we put it further down the length of the beam, the signal that would be generated by it would be much smaller because it would see less stress and strain. So we want to put it somewhere kind of obvious, wherever the maximum stress point is. All right, so let me hit you with some more things right here. The thickness of our structure, T, is going to be 5 microns. And then our piezo resistor dimensions. So we'll have the length of our piezo resistor is 20 microns. The width of our piezo resistor is 5 microns. The thickness of our piezo resistor is half a micron. It's made out of 110 silicon, which will have an electrical resistivity of 11.7 ohm centimeters, meaning that this is N-type. Another question that I want to ask you guys just conceptually here. The thickness of our beam is 5 microns. The thickness of our piezo resistor is only half a micron. Do you think that might be a good design or a bad design just intuitively? What do you feel? Good. I agree that it's a good design, Hannah. Maybe we should talk about why I would consider it to be a good design. And this is just reminding you guys of some stuff that we covered at the beginning of our class, right? So whenever we have a cantilever beam, and this is a kind of side view, we learned that here's our neutral line, like so, right? So whenever our beam is deflecting downward, we should see that the top half of the beam is in tension or is in tensile stress, and the bottom half of the beam is in compression, right? We've already talked about this. And so it would have a profile kind of like this, right? Where the closer we are to the surface, the more stress and strain we would observe. So if we were to make our piezo resistor too thick, so say thick enough to where it extended beyond the neutral line, some of that compressive stress would cancel out some of the tensile stress, and so we've effectively just wasted material because it's not doing anything. Another reason we might want to make it as thin as possible is because it's technically a different material. than what the beam itself is made out of. And so if we make it relatively thin, we don't have to worry about what that material interface is doing. Whereas if we made our piezo resistor dip down into deep into the bulk of this thing, it's going to influence the behavior, or potentially even worse, if we deposited our piezo resistor on top and it was thick and bulky, it would greatly change our stress profile towards the anchor. So having something thin and either sitting on the surface or embedded into the cantilever is typically the way to go to put in a piezo resistive sensor. Okay. All right, so tangents away. We're done. All right, so what I want us to figure out is what is the fractional change in resistance caused by a force of F is equal to 25 micronewtons acting at the center of the proof mass. So ultimately, we're looking for fractional change in resistance. So we've got a couple of different relationships, right? We can do gauge factor times strain, or piezo-resistive coefficient times stress, right? So I'm going to argue that based on the information that we have, we're probably going to use the piezo-resistive coefficient by stress relationship, okay? So what would our maximum stress be? So going back several lectures at this point, the maximum stress for a cantilever beam is given by the applied force times the length from the anchor point at which our force is applied times the thickness of our beam divided by twice the second moment of inertia for our beam. So let's break this down into a few more digestible things. Okay. So our force is just our force. We know that's 25 micronewtons. We'll sub numbers in there in a little bit. How far away from our anchor point is our? So 225 micrometers. So that's the length of the cantilever plus half the length of the mass. Absolutely right. 225. The thickness that we should use here is the thickness of our cantilever. And now we're going to have 2, and then we've got I, right? So this beam has a rectangular cross section like everything else we've dealt with. Hopefully you guys can remember that the second moment of inertia for a rectangular cross section is AB cubed over 12. We've used that before, where B is the direction of bending, A is the transverse direction. So I'm going to put a 12 up here. So A, in our case, would be the width of the cantilever, and B would be the thickness of the cantilever, yeah. And this is cubed. Just as a side note out here, I'll put I is equal to AB cubed over 12, which in this case would be WT cubed over 12. Just so that you see, I'm just not making shit up. So substituting in our numbers here, we would have 25 micronewtons times 225 micrometers times 5 micrometers times 12 over 220 micrometers, 5 micrometers quantity cubed. And if I did my units correctly, and I'll just assume that I did, this comes out to be 67.5 megapascals. So there is our stress. For our N-type piezo resistor, notice that we have a 110 thing. Our current is flowing in the longitudinal direction, right? Because of the way that I've drawn the resistors, the current's going to flow down the length of the beam and then back up the length of the beam. So the current is definitely flowing in the longitudinal direction. Our stress is also applied in the longitudinal direction. So realistically, we should only need to bother with the longitudinal piezoresistive coefficient here. So for 110 single crystalline silicon, we can say that pi L, the longitudinal coefficient, is 1/2 pi 11 plus pi 12 plus pi 44. So this comes out to be 1/2 times negative 102.2 plus 53.4 minus, plus negative 13.6. All of those coefficients have units of 10 to the 11 per Pascal. And so this bit comes out to be negative 31.2 times 10 to the minus 11 inverse pascals. And our fractional change in resistance, delta R over R, is simply pi L times T max, which comes out to be, let's see, so let me write this, negative 31.2 times 10 to the negative 11 per pascals, 67.5 times 10 to the 6 pascals, and then I'm going to do times 100% just to give this as a percentage. And it'll be negative 2.106%. So our piezo resistor experiences a change in resistance of a little bit over 2%, right? Due to the deformation of the beam. For what it's worth, this absolute change in resistance, so we could find delta R is just going to be pi L T max times R, where R is rho E L over A. And this would be the length of the piezo resistor and the cross-sectional area of the piezo resistor here. So this would come out to be negative 2.106%, which is pi L times T max, 11.7 ohm centimeters, excuse me. And then we'd have 20 microns, which is the length of our piezo resistor, 5 microns times 0.5 microns, which is the width and thickness. This translates to negative 19.712 kilo ohms. For what it's worth, the nominal resistance of our piezo resistor was actually 936 kilo ohms. Okay. So this is a fairly appreciable change, or something that we should easily be able to measure if the resistance of our piezo resistor is large enough. Okay, So I believe I mentioned in our last class meeting that the piezo resistivity coefficients are temperature dependent. So we're going to explore that temperature dependence here really quickly. So temperature dependence of pi ij. So for doping concentrations, less than 10 to the 17 per cubic centimeter, which is, you recall from Monday, the exact same constraints on the information in our table. Okay. Pi ij as a function of temperature is going to look like whatever the piezoresistive coefficient was at 300 degrees Kelvin times 300K over our temperature. Okay. So it's just a simple inversely proportional relationship with temperature. Yes. 17. Let me write that better. Yeah. For silicon, whose intrinsic carrier concentration is in the ballpark of 1.0 to 1.5 times 10 to the 10, 10 to the doping concentration of 10 to the 12 wouldn't make it particularly conductive. So 10 to the 17, I believe, as I mentioned in our last class meeting, would be what we would consider like a normal doping concentration that we weren't using for implants or something like that, that we needed to make highly conductive. That's when you get into the 10 to the 18, 19 range, which we would consider N plus or P plus material. Yep. So in addition to the piezo-resistive coefficient being temperature dependent, the resistivity is also a temperature dependent quantity. So in general, the resistivity increases with temperature as carrier mobility decreases. This is a nonlinear dependence, but for small temperature changes around 300K. So let me write this down. So for small temperature changes around 300K, then we have what's called a temperature coefficient of resistivity. And I'm going to use that subscript 1 because we're considering only a first order approximation where we're throwing away all of the higher order terms. And this is going to be approximately 0.015 or about 1.5% change per Kelvin. So let's explore this really quickly. Okay. So I want us to repeat our prior example. For a temperature of 305K. So effectively just a 5 Kelvin increase. So at this temperature change, so I'm going to call this pi longitudinal prime. So it's just something that isn't at the 300K that we were at previously, right? This would be negative 31.2 times 10 to the minus 11 per pascals times 300K over 305K. So all I've done here is I've taken that combined piezo-resistive coefficient for the fact that we're dealing with 110 silicon. Just for what it's worth, that was this thing right here. And I'm just multiplying it by 300 over 305 because we're now at a temperature of 305 Kelvin, right? So our new piezo-resistive coefficient comes out to be negative 30.689 times 10 to the minus 11 per Pascal. So slightly smaller, which is what we should expect because we have an inversely proportional relationship with temperature. So my change in resistance is going to be pi L prime times our maximum strain times rho E L over A. All right, let me do that down here. So this comes out to be negative 30.689 times 10 to the minus 11 per Pascal, 67.5. Let me write that as times 10 to the 6 Pascal. And then once again, 11.7 ohm centimeters, 20 microns, 5 microns, and 0.5 microns. So negative 19.389 kiloohm. So the change in resistance due to the change in piezo-resistive coefficient roughly or relatively small here, right? We originally had negative 19.712 kiloohms of change in resistance. Now we see negative 19.389 kiloohms change in resistance. So wasn't a huge deal. But let's see what happens if we deal with our change in resistance due to the resistivity, right? So let's call this delta R subscript T for change in resistance due to the temperature dependence of resistivity. We would find this by taking the temperature coefficient of resistance, multiplying it by the change in temperature, and then rho E L over A. So just our nominal resistance. So this is going to wind up being 0.015 per Kelvin times 5 Kelvin. And then we have that same 11.7 ohm centimeters, 20 microns, 5 microns, and 0.5 microns. And this comes out to a change due to our change in temperature of 70.2 kiloohms. So roughly, the change in resistance due to the change in resistivity is roughly 3 times larger than the change in resistance due to the piezo-resistive effect. Okay, so that can be pretty damn problematic because we either have to work at a very, very fixed temperature or we need to figure out some way to compensate for temperature changes, right? So that compensating for temperature changes things is done in a variety of different ways, okay? So let's talk about piezo resistance measurement schemes. Yes, ma'am. What part of my penmanship got too shitty for you to read? Okay. So let's call that one delta RP because it's a change in piezo resistive coefficient. And delta RT is because of a change in resistivity due to temperature. Yes. So effectively, yes. But what I wanted to illustrate here more real So you're 100% correct. So let's look at this thing just really quickly, okay? So when our beam is undergoing flexure because of that applied force on our proof mass, we should see that the nominal resistance of our piezo resistor decreases by 19.389 kiloohms, right? So that change in resistance only exists because we are deforming our piezo resistor by applying some stress, okay? The change delta RT for the temperature dependence on resistivity is just happening because we're at 305K. And it's a positive change in resistance. So as the temperature increases, the resistance will increase. Those net effects would be combined together, okay? The problem, as it were, is that the change in temperatures effects are roughly 3 times larger than what we're seeing due to our beam being deformed. So as a piezo-resistive sensor, this isn't working out so hot for us because any change in resistance that we're seeing due to the beam deforming is actually being significantly outshone by the change we're seeing because the temperature is slightly higher. So either we have to make sure that our device operates at just effectively 300 Kelvin so that we don't see any change in resistance due to the temperature coefficient of resistivity, or we need to find some way to make that term cancel out. Does that? Yeah. Okay. So let's look at piezo resistance measurement schemes. Piezo resistance. Schemes might not be the best word. Maybe methods would be better, but I like schemes. So one of the reasons why piezo-resistive sensing is so widely used in MEMS devices is because it's very trivial to convert that change in resistance into an electrical signal. If we force current through our piezo resistor, we will observe an output signal that is representative of our change, right? So the simplest scheme that we might see is one in which we literally have some DC current source, which I'm just going to call IDC. Here is our piezo resistor. So this is going to be just R naught, which is the nominal resistance, plus some delta R, which is the change due to the piezo resistive properties of the resistor. And we're going to measure our output voltage here. Okay. So we can look at our output signal just by using Ohm's law, right? So using Ohm's law, we would see that our output voltage V out is nothing more than our DC current IDC times the resistance R naught plus delta R. So that's the voltage that we're going to see at the output of our system. And let's explore this a little bit more, okay? So I'm going to take that IDC. We've got our R naught, and let's break down that delta R into our longitudinal piezoresistive coefficient times our longitudinal stress plus our transverse piezoresistive coefficient times our transverse stress, and then all of that gets multiplied by R naught. We can pull out a factor of R naught from this whole thing. So we would have IDC R naught plus IDC R naught times pi L TL plus pi T TT, like so. So we have essentially a DC portion of our signal. And then over here, we have a portion of our signal that is inversely proportional, temperature dependent, effectively, right? So just for what it's worth, what would our power absorbed, what would the DC portion of our absorbed power be? And the reason why I'm bringing this up specifically is because piezo resistive sensing is great, except that it constantly consumes power, right? Because we have to constantly drive a current or something like that through a resistor in order to make our measurements. So we have always, or we're always absorbing power with this particular form of sensing. For our capacitive sensing, if we had paid attention, we would have noticed that it really only absorbs DC power when the signal's changing. So what do you guys think? I hope to God you electrical engineering seniors can figure this one out. What's going to be the total DC power absorbed in this system? Exactly right. And then for what it's worth, we might be interested in the noise spectral density, which would be simply 4 kBT R naught in this case. So this resistance measurement scheme can be useful in some applications, but there are some disadvantages, okay? So since the change in resistance could be small, we might have to amplify our output signal. And one problem with that is that if we amplify our output signal, well, we're also amplifying our DC offset. And that could be problematic because depending on what our headroom requirements and all of that kind of stuff are, if our DC signal is a few volts, we're still just boosting things up when we might wind up with a saturated signal at the output of our amplifier or something like that. So could be problematic if the DC level on this thing is too high. The temperature dependence of the resistance R naught is typically stronger than the piezo resistive effect, which we talked about a couple of moments ago. So we would have to spend some time calibrating this system in order to take that temperature dependence into account, which the time it takes to do that is effectively costing us money. So there are other ways we might use to do this, which will eliminate some of those issues. Okay. So let's look at what's called single-ended sensing with a bias voltage. So single-ended ratiometric sensing is just a really fancy term for voltage division. Okay. So for this particular scheme, we might have something like this, where we've got some DC voltage. We have a reference resistor, R naught. And then we have our piezo-resistive sensor having a resistance of R naught plus delta R. And we take our output voltage here at the midpoint, right? So one of the critical aspects of this particular type of sensing is our ability to create a reference resistance. So just for shits and giggles here, if we scroll back up to the previous example where we had a cantilever beam based piezo resistive sensor, Our reference resistor would literally be made by just adding a piezo resistor into the bulk material that will not undergo any stress whatsoever. We would do it during the same fabrication process as the piezo resistor itself so that we guarantee that they are literally identical, right? So by embedding resistors into the bulk of our material, which isn't going to undergo any stress or strain, it provides us a reference that we can use to compare our signal to, and we'll see some of the advantages of that. Okay. So come back down here. So using voltage division, we can see that our output voltage V out is just going to be our DC voltage times R naught plus delta R over twice R naught plus delta R. And since R naught is much greater than delta R, we could use a Taylor series expansion. So our output voltage V out will be approximately our DC voltage times a factor of 1/2 plus 1/4 delta R over R minus, and so on and so forth, where we're only going to worry about those first couple of terms in our Taylor series. So this would come out to be 1/2 VDC plus 1/4, substituting in for delta R over R as pi L TL plus pi T TT, and then this is multiplied by VDC. So we still have a DC term, and we've got our signal that is dependent on temperature, but we don't really have to worry about the temperature change in our resistivity coefficient here, because both the reference resistor and our sensing piezo resistor will experience the exact same change. So those guys wash each other out. So we only see the effects of piezo resistance in this particular case. Okay. Our DC power consumption is going to be VDC squared over twice R naught, because we're just going to see those two resistors in series. So it's just the total voltage drop across the two resistors divided by the total resistance. And our noise spectral density measured at the output is going to be the square root of 4 kBT R naught in parallel with R naught. So effectively, to explain what's going on here, if I look into the output terminal at a small signal model for this thing, and I know you guys that had me for 335 and 336 are now having flashbacks, we would see our two resistors R naught effectively in parallel with each other, because we treat our large signal voltage VDC as if it were a small signal ground. So we would see R naught up in parallel with R naught down, which is why I have R naught in parallel with R naught for you guys that don't have a ridiculous electrical background like I force my PE undergrads to have. So R naught in parallel with R naught is just half R naught. So this winds up coming out to be twice KBT R naught. So we've eliminated the temperature dependence problems of our resistivity by this particular configuration. We've actually lowered our noise spectral density. but we've probably increased our power consumption. I say probably because it's not an apples to apples comparison because we don't know what IDC is or what VDC is. We're just using things generically here. All right. So let's look at yet another scheme. So this is what we're going to call differential sensing. With a bias voltage and there are two different ways that we can approach this. So our first case is we have a single piezo resistor. So we're going to incorporate what's called a Wheatstone bridge configuration here, which I think we talked about briefly when we're dealing with capacitance sensing, or at least we use this particular form, but we're going to have kind of a diamond shaped thing here. And we're going to have three reference resistors, R naught like so. And here is our piezo-resistive sensor. I'm gonna put ground down here. We're going to call this guy V1, call this guy V2, and our output voltage V out will be defined as V2 minus V1. So since, and I may be mistaken here because my memory is hot garbage, but I believe we've seen something like this before. What did it do when we saw this before? So when we were talking about our capacitive circuits, I believe it got rid of a constant term effectively. And that's exactly what it's going to wind up doing here. So just for what it's worth, if we find our voltage V2, we can find it using voltage division. It's literally just the exact same thing as our previous circuit, if we only consider the right-hand half, right? So this would be VDC times a factor of 1/2 plus 1/4 delta R over R naught from our previous derivation. V1 using voltage division. So it's going to divide evenly among those identical reference resistors. So this is literally just going to be 1/2 VDC. And when we take those two signals, V out is equal to V2 minus V1, the 1/2 VDC term cancels each other out, and we're just left with our DC voltage that we are applying times a factor of 1/4 delta R over R naught, which will be approximately 1/4 pi L TL plus pi T TT times VDC. Sorry, I'm running out of room over there to the right. But effectively, our output signal is only dependent on our piezo-resistive effect. So we've eliminated the DC signal, which means we've made our output signal easier to amplify. And we've also eliminated that temperature dependence on the absolute resistance because all of our resistances will increase by the same amount, which means it cancels out. So this is a pretty solid method. Our DC output, PDC here. So this is going to look like our DC voltage squared. And then we have effectively twice R naught in parallel with twice R naught. So this is just VDC squared over R naught. So we actually wind up consuming twice as much power as our simple single-ended ratiometric sensing or our voltage divider circuit, which makes sense because we have twice as many resistors, or we just have two voltage divider branches. So it should probably consume twice as much power as a single voltage divider branch. Our noise spectral density is going to be root of 4 kBT times 2R naught in parallel with 2R naught, which we already know is just R naught. So this is 4 kBT R naught. So our trade-off for eliminating that DC portion of our signal so that our output signal is easier to amplify is that we consume twice as much DC power and we're introducing twice as much noise. So let's look at, yes.
Just conceptually, I understand that this takes twice as much power, but I see that it also has more, we're also introducing more noise because we're using more power. So my question is, what's the trade-off? Why would we use this instead of just a single-sided sensing? Like it's more noisy, using more power. Is it more sensitive?
So the single-sided sensing contains a DC term. So we have a DC signal that if we need to amplify our output, that is also being amplified. I don't know how familiar you are with electronic amplification or anything like that. So let me just do a quick aside here. Let me go several pages down, okay? So let's just say that we're gonna amplify our signal using an op amp, which is the most common way to amplify literally any electrical signal, okay? So an op amp is an example of a differential amplifier, and generally speaking, we would do this using a negative feedback configuration, okay? So actually, because I'm doing negative feedback, this guy should be down here. My apologies. So this is our feedback resistor. This is just some resistor I'm going to call R1. And not to get too far in the weeds, we're going to apply our input signal here, right? So this particular configuration is what's known as a non-inverting amplifier. And so the output voltage is simply 1 plus RF over R1 times whatever our input voltage is. So if our input voltage contains a DC portion, then that's also going to get amplified. Now, why that could potentially be problematic is because it depends on how large that DC signal is, okay? So in the lower level circuits courses and all of that kind of good stuff, this is something that tends to be glossed over, but we cover in electrical engineering 223 or circuits 2, so their first sophomore level circuits class. The power supply voltages that are used for amplification are critically important. So we're going to have some voltage here, VCC plus, and some voltage here, VCC minus. And essentially, the output voltage of our amplifier system is limited to fall between those two voltages. So we can never have a signal that's more positive than VCC plus, and we can never have a signal that's more negative than VCC minus. So that DC offset and the fact that it's also going to be amplified might push the output of our system to a point where the amplifier effectively becomes saturated. And what that means is that any increase in input signal does not cause a correlated increase in the output.
It would be like having a threshold on the output, like we wouldn't be able to detect that at a certain point.
Exactly right. So we potentially might not be able to see what that change due to piezo resistance is because we're amplifying that input, the DC portion of that input signal as well. This guy here that doesn't have a DC portion of the input signal, while it is twice as noisy and twice as power consuming, we don't have that problem. All we're amplifying is the output that is dependent on the piezo resistance. Okay. So the second version of the differential sensing or double-ended ratiometric sensing is just using effectively two piezoresistive sensors, okay? So it's going to look like almost exactly the same circuit, but we are going to have a VDC here. So we're going to put a piezoresistive sensor here. So we've got an R naught plus delta R. Here's an R naught. Here's an R naught. And here's an R naught plus delta R, like so. Once again, this is V1. Once again, this is V2. And let's figure out what's going to happen here using voltage division real quickly, right? So our output voltage is still just going to be V2 minus V1. V2 is the exact same thing that we saw earlier. So VDC R naught plus delta R over twice R naught plus delta R. V1 from voltage division is going to be R naught over twice R naught plus delta R. And then when we take the difference of these two things, we're going to wind up having VDC times delta R over twice R naught plus delta R. But since R naught is so much greater than delta R, this is going to look approximately like VDC times delta R over twice R naught, or 1/2 VDC delta R over R naught. It could be written as pi L TL plus pi T TT, like so. Okay. So let's compare this signal with this signal. What's the difference? Try to make my screen smaller. Exactly right. So if we add two piezo resistors, we effectively double our output signal, meaning that we may not have to amplify or provide as much amplification to be able to see the effects of our changing piezo resistance. Now let's look at the power consumption and the noise again. So for our power consumption, this is going to look like just two voltage divider circuits in parallel again. So it's effectively going to have the exact same power consumption as our previous double-ended scheme. So VDC squared over R naught. Our noise spectral density is then going to be root 4 KBT R naught. So this particular scheme provides double the output signal, same power consumption, same noise as the prior one. The arguable disadvantage here is that we have to be able to efficiently electrically connect this thing with the two piezo-resistive sensors in order to make it work. So this one's trade-off comes at effectively the expense of a more complicated fabrication process. Okay, so one last sensing scheme, and then we'll move on to something else. So this one is known as differential sensing with a bias current. And effectively, it's going to be almost the exact same thing as our previous Wheatstone bridge configuration, but instead of having a DC voltage source up at the top, we're going to have a DC current source. So here's our current source. Here's an R naught plus delta R. Here's an R naught. Here's an R naught. An R naught plus delta R. So we can see that these paths contain identical resistances. So our current IDC should literally just divide evenly among these two paths, right? So from this, V2 is just going to be 1/2 IDC times R naught plus delta R. V1 is going to be 1/2 IDC times R naught. And so our output voltage, V2 minus V1, is just going to be 1/2 IDC times delta R, or 1/2 IDC R naught pi L TL plus pi T T T. Um, the DC power consumed by this guy, so that's just going to be IDC squared times R naught, because we have two parallel paths of twice R naught. Yeah. And our noise spectral density would be root 4 KBT R naught. So this is effectively just using a current source to get a similar result to the previous where we had a voltage source. All right. One last thing that I want to talk about. We have time for it. Oops. Is a specific type of noise that we'll see when creating piezo resistors, and this is what's called shot noise. Okay. So I'll start it here. So shock noise occurs due to random fluctuation in electrical current across a potential barrier. And I'm going to put in parentheses here, such as a metal semiconductor contact like those used to inject currents into a deposited, go away, Dropbox thing. So essentially, there is, and this is another place where the electricals are going to have flashbacks of me talking about metal semiconductor junctions and all that kind of jazz from 335. But essentially, there is a small, what's called a contact potential whenever you have two different materials interface with each other. And because of that contact potential, we are going to see current fluctuations, which are going to show up as a form of noise in our piezo resistors. And it is completely and utterly unavoidable because we need to connect to our piezo resistors with wires or good conductors and then have, high resistance something to act as the piezo resistor itself. Okay. So this shot noise is mathematically modeled as a current as the square root of 2q, where q is the charge of an electron, times I, the amount of current. And we could turn this into a voltage noise signal by simply saying that our voltage noise spectral density is just our current noise spectral density. Let me move that dot below. Times our resistor value, or in other words, 2qi times r squared. This shot noise can be greater than thermal noise. Okay. So for example, let's say that we have a 1 kilo ohm piezo resistor carrying 1 milliamp of current. Okay. Our thermal noise would be simply the square root of 4 kBTR, right? So if I plug in the numbers for that, I wound up getting 4.069 nanovolts per root hertz. So that's what my noise spectral density, or my white noise spectral density value is. For my shot noise, that's going to be root 2 qi r squared. And this comes out to be 17.9 nanovolts per root hertz. So we can see that the shot noise is about 4 times greater than our thermal noise. So this is just something else that we need to take into consideration if we wanted to use piezo-resistive sensing. All right, that finishes up my notes on piezo-resistive sensing, and conveniently enough, we only have 2 minutes left of class, so this seems like a really good place to stop.